Hello. So in this video, we're going to talk about Haberman's section 3.5, which talks about term-by-term integration of Fourier series. And so, right, in 3.4, the focus was term-by-term differentiation, right? And so the question was, right, so if you have a function f of x, which you write as a Fourier series, I'll just write it like this, right? Last time the question was, well, if we differentiate f of x, and then look at that Fourier series, is its Fourier series the same as if we differentiated term by term? Okay? And so the observation is, well, not always. Here, we're going to be concerned with kind of the opposite operation, where now we're going to ask, well, if we integrate, on the left, if we integrate the function and we look at that Fourier series, is that Fourier series what we get by integrating everything term by term? Okay, so that's the focus of this, this section. Okay, and so we'll start by just stating kind of the main result, which says, what you get if you integrate a function and then you integrate its Fourier series term by term. We'll get some examples of ways that we can use this in practice, and then we're going to give a short proof of the main result. In this case, the proof is just essentially computing Fourier coefficients and showing that, yes, they do match up with what we want them to be. Okay, so what is the main result about integrating a function and integrating its Fourier series term by term? So the main result is the following. So if your function is piecewise smooth, if your function f of x is piecewise smooth, then its Fourier series can be integrated term by term. You're going to end up with a convergent series. And that convergent series will converge to the integral of the function that you started with. Okay? Even if your original Fourier series has jumped discontinuities. Okay? And so, okay, great. What does this look like written out? Right, well, here's our given function f of x, okay? And we're writing f in terms of some Fourier series, okay? And so then what we're interested in is the function that we get by integrating, right? So this is the function that we care about. How do we get this? Well, we integrate our function from the lower bound negative L up to some point y, right? So that this integral is a function of y. And so, great, that's what kind of this piece looks like upon integration. What does this piece look like upon integration? Well, right, set up the integral, distribute across the sum, etc. The claim is that this integral is equal to the series that we get here. Okay? Or in short, if you want to integrate a Fourier series, you're free to do so term by term, which isn't always the case with differentiation. Okay. Cool. Okay, so, right, what happens if we actually integrate? Well, let's see, so there should be an equality right here. Okay, but right, so this was the function that we were integrating. This is what we get by term integration. Okay, so the integral of the constant term up to y is going to give you this expression, right? A naught constant times x, a value between these bounds. So this should actually be plus. There you go. Okay, so that's that integrated. This you integrate, you're going to get this. And keep in mind that, right, so technically, the integral of this is going to be a sub n L over n pi sine of n pi over L x evaluated between negative L and y, right? But when you plug negative L in here, this is going to be a sub n L over n pi sine of n pi over Ly minus a sub n L over n pi sine of minus n pi, okay, right? And this term right here, this is 0, okay? So this integral, we just get this piece, which is what we see right here. Okay, this other integral, when you do these same steps, right? Well, here you're going to have a cosine instead of a sine, and cosine of minus n pi is cosine of n pi, right? And so then that's where this term comes from. Okay? Otherwise, we evaluate at y, and that's that. So maybe written out explicitly. So this integral becomes this. This integral, we get this whole thing. Okay? So if we just integrate the series term by term, we end up with this series. Okay. Right. And again, the claim is that this series is exactly equal to this integral. Okay, so one thing to note, right? So there should be a plus there. If we take this term, right, and split it up as a naught y plus a naught L, okay, and then look at the context of everything else, right? So a naught L is a constant term, right? Constants appear as cosine of 0. Okay, so constants are allowed in these trig series. Over here, right, we have a bunch of these constants showing up, and we're summing over these constants, but they're all constants. So when you sum up all these constants, you just get, right, another constant, and so then that's going to be constant. Otherwise, we have sine pieces, we have cosine pieces. Those are all trig functions, so that's all fine and well. The issue is that this first piece, a naught times y, right, or if you change variables so that you're working with x, this piece is not a trig function, right? It's not a constant or sine of something or cosine of something, okay? So technically, this expression right here, this is not a Fourier series because this piece right here is not a Fourier kind of building block, okay? And so that's why in the statement over here, right, when we talk about kind of the integrated Fourier series, we're not necessarily calling this a Fourier series, right, because it may not be. But then the question is, right, well, when can it be? Or can we rewrite things in a way so that we do end up with a Fourier series? And so in this case, the answer is, well, yes. The function kind of just y, or again, if you change variables x, right? This function we can write as a Fourier sine series. Okay. So the question is, why are we writing this as a Fourier sine series and not a cosine series? Well, the short answer is that, right, since we're looking over the interval negative L to L, what does this function look like? It just looks like that. This is an odd function, right? And so since it's odd and not even, right, we expect and we get that its Fourier series is only going to consist of sine terms, okay? And so that's why we're free to only take this kind of sine expansion for y. Okay, but what we can do is, right, well, take this series for y and then plug this in right there, recombine things, and then we should end up with a Fourier series. Okay, so what does that look like? Well, oh boy, let me just type it. So this was our original expression, right? A naught times y plus L plus kind of the integrated pieces. Okay, so what we're going to do, let me correct these. So what we're going to do is we're first going to split this up into kind of this a naught y piece, which is coming down there. This a naught L piece, we're moving over there. And then finally, we're going to take this sum of constants here and relocate these pieces over here. Okay. So what we've done here, right, is we've kind of rearranged things so that in this infinite sum right here, we just have the sine functions and then the cosine functions. Okay. And then we've collected all of the constant pieces over here. Okay, so this is going to be our constant term. These are going to be our sine and cosine terms. And so now all we're left with is this a naught y. Okay. Right, but here, what we're going to do is substitute in this series, right? So sub sine series in here. Okay. And so now in this expression, right, the only thing we've changed is plugging in what the sine series for y looks like, right? And this was this expression right here, right? We've plugged this in. Okay. And so again, we have all the constant terms, a sine series plus a sine and a cosine series. Okay. And so at this point, what we can do is, well, right, if we split this up into a sum over the sines and then a sum over the cosines, right? Well, here we have a sine of n pi over ly, and here we have a sine of n pi over ly, right? So what we can do is combine kind of like terms and then combine these two sums, okay? And so then the resulting piece is going to be, right, again, our constant piece plus this combination of sines, right, where this thing kind of goes there and this thing shows up right there. And then we're left with the cosine pieces that don't change. Okay. So now this last expression right here, this is, I should make that, I should, right, this thing right here is the Fourier series for y. Okay. And it is a Fourier series because, right, we've expressed things just in terms of constants, sines, and cosines. Okay. Cool. Okay. So one note is that, right, in all of these steps before, we were integrating from negative L, I guess, to y. Okay, but right, we've integrated from negative L to kind of the variable that we care about. But assuming that this is all well and good, it actually doesn't matter where we integrate to, right? Because, right, so these are the integrals we're working with. Maybe you can write it out, right? So the integral from negative L to x, this is the integral from negative L to a, plus the integral from a to x. Okay, so in this context, if we want to integrate from any other bound a, so for example, if instead of integrating series from negative L to whatever, we want to integrate from 0 to whatever, we're allowed to do that because we can write this integral from any other starting point in terms of two integrals that start at negative L. Okay. So our steps before say, well, if we're integrating from negative L to where we care about, you know, sure, that's all well and good. And so then we can combine those results to integrate from any other point, like a equals 0, and still things work out. Okay. And so in these examples, we'll actually do that. We'll integrate from 0 to the variable we care about, just because plugging in 0 is going to make things a little nicer to work with. Okay. Cool. So let's see some examples or kind of instances where this might be useful. So the main, use for some of these things are constructing new series from old. Okay? And so an example of that might be, well, you have a function that you want to compute the Fourier series for, but for whatever reason, kind of the integrals that would give you the coefficients are just messy, nasty, what have you. But you know the Fourier series for kind of the derivative of that function. So what would be nice is if you could integrate the Fourier series of the derivative to get the Fourier series of the function that you actually care about. So as an example of this process, so here's a Fourier sine series for 1, the function 1, and so I'll say Fourier sine series, right? If we had cosine terms, the Fourier series of 1 would just be 1, but we're working here with the Fourier sine series, okay? And so if we integrate each term from 0, say, to our dummy variable, in this case, x, right? Well, integrate this left side, right? Integral of 1 is x, plug in the bounds 0 and x, you're just going to get x. Integrate, right, sine of n pi over lx dx. This is going to be minus L over n pi cosine n pi over Lx. And if you evaluate between 0 and x, this is going to be between 0 and x. And so this is going to be, so L over n pi cosine of n pi minus cosine of n pi over L x. Right, and so this expression is what's going in there, what's going in there, what's going in there. Right, we're getting these squareds because we have a 5 up here and a 5 down there, for example, etc. Okay, but this is what we get by integrating term by term. Okay, cool. And so now what we can do is kind of simplify it a little bit, or I might say collect like terms. And so as before, what we're going to do is first collect all the constant pieces, right? And so the observation is, well, in the series right here, we're going to have an L over pi plus L over 3 squared pi plus L over 5 squared pi, etc. So we're just adding up all these constant terms. And so what we're going to do is collect all of these constant terms and just kind of keep them in this piece over here. Likewise, we're going to collect all of the cosine pieces and then collect those in a series of their own. Okay. And so we also, what do we also do? Well, we pulled out an L over pi from each of these terms, brought that up front, so that gives us our 4L over pi squared. Each of the cosine pieces has a negative in front of it, so we pulled all of these out in front. Okay, but otherwise, all we've done here is right, rearrange the terms. Okay, and so okay, so then the questions are, well, what are the actual coefficients for this function x? Well, the coefficients a sub n, we can read those pretty easily, right? So distribute this over, you're going to get something like, right, a sub n is going to be negative 4L over n squared pi squared for n odd, and then 0 for n even, right? And so we compute these coefficients just by looking at the coefficients for the cosine pieces. Okay. Great, so that's super easy, right? And this also saved us the effort of computing, right? A sub n is 2 over L integral from 0 to L of x cosine of n pi over L squared dx. Okay, so I guess this integral isn't too bad, but right, it did save us that effort. Question though is, right, well, sure, this is our constant term, but we don't necessarily know how to deal with that. I mean, probably converges to something, but what it actually converges to, good question. But the observation here is, well, right here we're working with the cosine series. And so we know that for a cosine series, well, a sub 0, this is going to be 1 over L, the integral from 0 to L of the function we care about, right, which in this case is x. Okay, so this expression right here should just be equal to this integral. Okay, right, so because we have another formula for the constant term, and then we actually evaluate this, right, we get what the constant term is L over 2, right? So comparing this constant term with the series or the constant term in that series representation a second ago, we get that L over 2 is equal to this. Okay, and so if you want a fun little identity out of this, well, say move this to the other side, you're going to get what, pi squared over 2, sorry, pi squared over 8 is equal to 1 plus 1 over 3 squared plus 1 over 5 squared plus dot, dot, dot. Okay. Neat. Cool. Okay, but if we're just interested in Fourier series, this also tells us that, well, the constant term is just L over 2. And so now we actually have our Fourier series and we have all the coefficients we might ever want to compute. Okay. Cool. Okay, but we can also repeat the process, right? So say we want the sine series for x squared. So one way we could do that is, well, just compute, right? So the coefficients, ordinarily these would be 2 over L integral from 0 to L of x squared sine of n pi over Lx dx. We are super, they're getting a little more terrible. But anyways, right, this is how we compute the coefficients kind of directly, right? This is a definition of the coefficients. But what we can also do is integrate the cosine series we had before. Okay? And so in this case, what do we get? Well, if we integrate term by term, right? So on the left-hand side, we're just going to get x squared over 2, right? Because we're integrating x from 0 to, say, x. On the right-hand side, the integrals we have to worry about are the integral from 0 to x, in this case of cosine of n pi over Lx dx, which is going to be L over n pi sine of n pi over Lx evaluated between x and 0. Right, and of course, plug in 0 there. Sine of 0 is 0. So then this is going to become L over n pi sine of n pi over Lx. Right, so each of these pieces, they just integrate to kind of these corresponding sine pieces. Okay. For each of these integrals, we're going to pick up an L over pi, which we can factor out to, right, here we have an L over pi squared. Over here, we have an L squared over pi cubed, right? So the extra L over pi is coming from integrating each of these. Otherwise, in each of these integrals, we have this n, this 1 over n that's coming in front. And so for the original series, we had a 1 over 3 squared, 1 over 5 squared, etc. And so that's where we pick up a 1 over 3 cubed, 1 over 5 cubed, etc. Okay. Okay, so yeah, so that's integrating this piece and then all of these pieces, right? The only other piece we have to worry about is the integral of L over 2. That's just going to give an L over 2x. And so if we integrate term by term, we're going to end up with this expression, right? X squared over 2 is going to be equal to L over 2x minus this Fourier sine series. Okay. And so again, right, this thing right here, this is not necessarily a Fourier series, right? Because x is not a trig function. So one way of interpreting this is to say, well, move this L over 2x to the other side, right? On this side, we're going to have an x squared over 2 minus L over 2x, okay? But then on the right-hand side, we're just going to have a sine series, okay? So one way to maybe interpret this result is that, well, this tells us what the sine series of this function is. Which, you know, sure, that tells us something. Another option or another interpretation is, well, if we plug in what the sine series for x is, right, which we've already computed, where was it? Right here, right, use this expression for the sine series of the function x. Right, so if we plug in the sine series for L over 2x, then this is going to be a sine series. This is a sine series. We can combine the two to get another sine series, and then that will tell us what the sine series for x squared over 2 is. Okay. Right, so depending on what you need to use the stuff for, right, you have either interpretation that's fine and valid. But the thing to keep in mind is that just by integrating, you don't necessarily get a Fourier series, right? Because you're going to have terms that might mess it up. In this case, this term. Another possibility is, for example, if we got something like, I don't know, some constant appearing on this right-hand side, well, constant terms, they're not sine terms, right? Constants correspond to sine or cosine of 0. But here we're working with the sine series, which don't include the constants as building blocks. So if we wanted to interpret this as a Fourier series, we'd have to plug in 1, the Fourier series for x, 2, the Fourier series for a constant. And here, since we're working with sine series, we'd probably be plugging in the sine series for the constant. But just another, I don't know, thing to be careful of. Cool. Okay, right, so yeah, so generally integrating Fourier series is great when you want to compute kind of a new Fourier series from one that you already know. Especially if computing the coefficients directly is going to be bad for whatever reason. Yeah, okay. And so the last part of this is going to be, well, right, where does this formula come from? Why is it true? And how can we be sure that, right, we can integrate term by term? Okay, and so here's how we're going to go about it. So consider kind of the, when I say the antiderivative of our function f of x, but right, we're actually evaluating between bounds. Okay, so let capital F of y be the integral of f of x from negative L to a given point. In this case, we're calling y. Okay, and so we're using a different variable here, just so we don't confuse kind of the argument of this with the argument of this. Okay. For f of x piecewise smooth, capital F is going to be continuous. Okay. At least in the interval negative L to kind of right L inclusive. Okay, so let's start plugging in values. Well, if we plug in negative L, right, this becomes the integral from negative L to negative L, right? So we're integrating over a single point. we're not getting any area. And so capital F of minus L, that's just 0. Plug in capital L, or plug in L, right? So then capital F of L, that's the integral from negative L to L of f of x dx, right? But here the observation is, well, for the Fourier coefficient a sub 0, this is going to be, right, 1 over 2L, the integral from negative L to L of the function that we care about, dx, right? So this is the formula that we're using if we want the constant term in the Fourier series for a function, right? So move this piece up here, it's going to be 2L a naught. And so again, so capital F of L is this constant term. Okay. But note that, right, so 2 and L are non-zero, but a sub 0, that constant term for the Fourier series, that may also be non-zero. Okay. So capital F of L may not be 0. Right, so even though F is continuous, and so I should highlight this is continuous for negative L less than or equal to Y strictly less than L. Because the endpoints don't agree, if we take the Fourier series, right, the value of the series at Y equals L, that's going to be the average of the left and right limits. In this case, the left limit will be f of negative L, which is 0. The right limit will be f of L, which may not be 0. And so the Fourier series may be discontinuous at Y equals L. Okay. So what we're going to do is we're actually going to consider kind of a translation of the function, right? So suppose f of L looks something like, so it's going to be 0 right there, and we're integrating little f, so it might be something like that, and then the value at Y equals L is going to be, say, up there. Right, and so what I was saying before, right, the value of the Fourier series, well, if we take this periodic extension, it might look something like that, etc. And so then the value at L is going to be halfway between the two limits. Okay, but what we're going to do is we're going to say, okay, well, take the straight line connecting this point to that point. It's going to look like that. This straight line is going to be exactly a naught times y plus L, right? Because if you plug in y is equal to negative L, this becomes 0, so you get 0 out of this. Plug in y equals L, you're going to get a naught times L plus L, which is a naught times 2L, which is exactly equal to capital F of L, right, from what we had here. Okay. And so this is a straight line, right, because it takes, I mean, if you want to, you can explicitly write it out as slope times y plus kind of that y-intercept, but anyways. Okay. So if we consider the function capital F of y minus this linear piece, right, well, what do we end up with? Plug in negative L, you get f of negative L minus a naught times negative L plus L. This is 0 by definition of capital F of L. This is 0 because minus L plus L is 0. So g of negative L is 0. Okay. Plug in L, right? Well, f of capital L, right? That's some value. Okay. So this is actually, right, this was 2 a naught L. Plug in L for y, you're going to get a naught times L plus L. So this piece is exactly 2 a naught L. This piece was 2 a naught L. So the difference between these two is just 0. Okay. Okay, well, so g of y, right? It's a linear combination of two continuous functions, so g of y is also continuous. And moreover, since the left and right endpoints of g of y are equal, right? If we take the Fourier series of g of y, because g of y is continuous and its endpoints are equal, the Fourier series of g of y will be exactly equal to g of y, right? So usually if we were computing these Fourier series, right, we'd say, well, this thing right here is a Fourier series, so we would just have this tilde right here, meaning, right, the Fourier series of g of y is this thing. But because this is continuous and the endpoints are equal, we actually have equality between the function we care about and the Fourier series. Okay. So, right, this is the Fourier series of this difference, and this Fourier series is exactly equal to this difference. Okay. Okay. Great. Well, so now let's compute some of the coefficients. Right. Okay, so, right, this is the Fourier series we're interested in. Let's start computing the coefficients for the cosine pieces. Right, so assume n is non-zero. Question is, what is a sub n? Well, right, this is the function that we want the coefficients for. Multiply that by cosine of n pi over l y, integrate from negative L to L, and then kind of normalize by 1 over L. What we're going to do is split this up so that we have, so f of y, so, right, what we're going to do kind of, right, first step is write y plus L, write this as f of y minus a naught L, right? So distribute this to that, and then just keep track of this and that, minus a naught y. Okay, and so then here we're going to split up how we're computing these coefficients so that we're computing the coefficient of this, and then we're computing the coefficient of this, right? So one way to maybe interpret that is, well, the Fourier transform, or computing these Fourier coefficients, that's a linear operation. So if we have, right, a sum or difference of functions and we want their coefficients, we can just compute the coefficients individually and then take the sum or difference. Another way to interpret it is, well, just distribute this cosine of n pi over ly to the various pieces, reorganize, split up these integrals, and you're going to get this expression. Okay. Okay. And so I'll say, so technically we could also consider a third integral, right? Plus 1 over L integral from negative L to L of a naught L cosine of whatever dy. We could do that, and that wouldn't change kind of the steps coming up, but we'll keep it like this. Okay, so the observation here is that, well, this second integral is 0 because y is an odd function on negative L to L, right? Fact that we stated earlier. So if we want the coefficients a sub n, how do we compute those? Well, we just compute these integrals. Okay. So let's do that. So the coefficients a sub n are equal to this. Here we're going to use integration by parts, right, which again takes the form, so the integral of u, and so there should be a dy here. But integration by parts takes the form u dv is equal to uv minus the integral of v du. So here we're going to let this function be u. This function is going to be dv. dy. So if we differentiate this, we're going to get, right, du is the derivative of this with respect to y. And then we also have this dy because we need that dy in the integral, okay? Right, and derivative of constant is 0. So this is what we want, right? But the observation here is that, so this should be a y. Right, well, we defined f of y as the integral from negative L to y of f of x dx. So, right, it's the fundamental theorem of calculus. The derivative of capital F is going to be little f. And so then this is what gets us that. Otherwise, for integration by parts, we need the integral of this thing, and then, right, integral of cosine, sine. We also need to bring this out in the right way so that, right, is this correct? We'll take the derivative of this. Do you end up with this? The answer is yes, so we're good to go. Okay. Okay, right, but just integration by parts to actually compute what these coefficients are for the integrated thing. Okay, so integration by parts, right? So this is uv minus the integral of v du, where technically du is f of y dy, but in any case, plug in the pieces, evaluate. So here, we're plugging in L and negative L in place of y everywhere here. Right, but keep in mind that when you plug in, right, so sine of n pi over L times L, it's going to be sine of n pi. This is going to be 0. Plug in negative L, you're going to get sine of n pi over L times negative L, which is sine of negative n pi, which is again 0. Right, so it doesn't matter what this is, right? This term is always going to be 0. And so for that reason, we could have ignored this minus a naught L when we perform integration by parts. But yeah, anyways, okay. So, so this whole term is 0. Otherwise, here, right, well, what does this look like? We have our function f of y times sine of n pi over Ly. This piece looks a whole lot like, right, the Fourier coefficient or the sine coefficient for the function f. And so explicitly, right, this thing right here, let's see. This is going to be 1 over L b sub n. Or actually here, let me write it. Okay, let me phrase it like this. Right, b sub n is equal to 1 over L integral from minus L to L of f of x times sine of n pi over L x dx. Okay, and so the observation is, well, here we're picking up this little this b sub n. My hesitation is because there's a 1 over L that's missing, but this 1 over L over here, this really should be multiplied by everything. Okay, so I just didn't distribute it in this integration by parts. But if we distribute it, right, so take this 1 over L, multiply it by the first thing. First thing is 0, so that doesn't really matter. Take this 1 over L, multiply it over there. What do we end up with? Well, we're going to get where should I write it? So here should be a 1 over L times L over N pi, and then my sign in front. And so then this 1 over L and then this piece is exactly the definition of B sub n. There we go. So plug in this times this is equal to B sub n. That's where this B sub n comes from. Otherwise, we have a minus L over N pi that goes there. Okay. So the cosine coefficients for this kind of function g of y, these cosine coefficients are essentially what we get by integrating the sine coefficients. Okay. And so for similar reasons, if you take this, if you start computing what the coefficients b sub n should be for the function g of y, right? Well, you plug this in, move things around, perform this integration by parts. You're going to get that these coefficients are exactly L over N pi times, right, the cosine coefficients for little f. Okay. Great. Okay, so that gives us almost everything, right? And so, oh, right, again here, right, so what are we trying to compute? We want g of y, which is a sub 0 plus the sum, a sub n cosine of n pi over L y plus the sum, b sub n sine of n pi over L y. Okay. So at this stage, we've computed a sub n and b sub n, right, from the last slide. And so the question is, what is that constant term? Okay, well, so here we observe that, well, if we want the constant term, let's plug in g of L, g of capital L, or okay, plug in capital L, so we get g of capital L. And we know that g of capital L is equal to 0. So this thing right here, this is 0. Plug in capital L here, right? Cosine of n pi, or sine of n pi over L times L, that's sine of n pi. All of these terms are going to 0. So we're left with a sub 0 plus the sum of a sub n cosine of n pi. And so that's exactly what's written right here. Okay. And so now what we do is we observe, well, right, these a sub n, right, we just computed those. A sub n is equal to this thing right here. So plug this in, and we're going to get this expression, okay? And so then this says, well, what is a sub 0? That's equal to the sum from n equals 1 up to infinity of b sub n L over n pi cosine of n pi, okay? Okay, so plugging this into this expression, what we can do then is kind of bring this piece over to the side, or sorry, bring this piece over to the cosines, and that's what happens there. Otherwise, recall that g of y, this was f of y minus a naught of times y plus L. And so here what we do is we can move this to the other side, plug in for a sub n and b sub n, and then in the end, we're going to get this expression for capital F of y. So, right, the integral of the function we started with, f, little f, the integral of that is exactly equal to this series. Okay? Keep in mind, though, that this is not a Fourier series because this is not one of the basis functions or kind of the building blocks for a Fourier series, right? So if we want a Fourier series, we have to deal with this non-Fourier piece. But if we don't even want to go there, we can just say, well, it doesn't matter because we have an equality here. These two sides are equal. Yeah, so that's integrating Fourier series term by term.